Hello, this is Mariam Qasim, and this is my third lab for Physics 2211, Black Hole. Here we have the index. We'll be having an introduction, we'll explain the physics principles, we'll introduce the code for part 1 and part 2, and then we'll have a discussion at the end. For our introduction, the purpose of the part 1 of the code was to model a star orbiting a black hole of unknown mass using low script and to use the data to find an accurate value of the black hole's mass. For part 2, the purpose was to find the velocity required for the spaceship that is launched from a planet orbiting the black hole to near the black hole and escape the system. Our aim was to find an accurate mass for the black hole by taking an average and to get the spaceship as close as possible to the black hole without crashing. Here's our main result. We found the mass to be 1.41 e34 kg, and we found the velocity to be negative 5 e7 1.8 e6 0 meters per second. Now, for the physics principles, there are two main laws. Newton's second law, which states that the net force is equal to the rate of change of momentum, which can be rewritten to find the velocity update formula and the position update formula. Note, we're going to use the parallel and perpendicular components of the net force in this lab. We also have the gravitational force formula, which is negative g mass, large mass, small mass over r squared multiplied by r hat. It's also important to note that we're making the assumption that the gravitational force is the only force acting, and therefore it's the net force. Like no other forces are acting on our system. For part 1, it's important to note that our system is a star and our surroundings are the black hole. I first set counters to 0, so I'm able to calculate the average at the end. I then changed the momentum and velocity, the momentum values to the mass, multiplied the initial and final velocities. We then found delta V and delta B by minusing the final velocities from the initial velocity by minusing the initial velocity from the final velocity and doing the same for the momentum. And then we find dp dt by dividing delta P by delta T, and then we set F net to dp dt because, as Newton's second law states, for the F net is equal to the rate of change of momentum. We could have also wrote F net as the mass multiplied delta V over delta T. We then found the d magnitude P over dt, and that is multiplied by P hat, which is the parallel component of the F net force as shown on the right in the second bottom equation. And then we use that to find F perpendicular, and that's simply by minusing F parallel from F net. We then use the gravitational force formula to find the mass, and I made sure to update my counter so I'm able to calculate the average at the end. Made sure to print it out as well at the end to make sure. Here's my arrow scale. We trialed and error until we found the arrow scale fitting for the results. And here are the results for part 1. We found the average mass to be 1.41 e to the 34. For our second part, it's important to note that our system is the ship, while the surroundings are the black hole and the planet. We first updated the black hole's mass to 1.41 e to the 34, which is the mass we obtained from part 1. We then added a random value for the ship's speed until we tried and error later on to find an accurate value. I then made sure to set an R minimum value to a very large value to find the shortest distance to the black hole. I found the position vector, I minus the position vector of the black hole from the planet, because our system minus our source is the change in R, and then use that to find the force of the black hole on the planet using, again, the gravitational force formula. We then made sure to add the forces to find the F net on the planet, and we did the same for the ship. However, this time, instead of using the gravitational force formula, I just changed the sign of the position vector and the force on the planet, simply because they're the same in magnitude but in opposite direction. We then updated both our velocities and position vectors while making the assumption that V average is equal to V final. I then made sure to update the minimum, and that's by using a simple if statement to find the minimum distance. Here are the results of my second part. On the left is a zoom of my results. We found the shortest distance to be 2.23 e to the 8. Moving on to the discussion, we first have the possible sources of error. Since the lab is completely computational, there aren't a lot of possible errors. However, possible source could be the rounding over to constant, or the fact that our time was short, so we didn't find a very accurate value of mass. Now let's identify the differences between the net force and the rate of change of momentum. The net force is the sum of all the forces acting on the system. The parallel component is in the direction of motion, and the perpendicular component is in the direction perpendicular to the motion. The net force is also equal to the mass multiplied by acceleration, which can be rewritten as the rate of change of momentum. Since momentum is mass multiplied by velocity, it is easier to calculate the rate of change of momentum rather than the force. Next, let's talk about the velocity required to have the spaceship orbit the black hole. After trial and error, I found out that the velocity has to be in the same direction as that of the planet, while being slow enough to stay in orbit yet fast enough to avoid crashing. Here's a video of my findings along with the associated value of V. We found V to be 0, 1e7, 0. Here we have the magenta line showcasing the spaceship. That's it for my lab. Thank you for listening.